Hello, everyone, and welcome our speaker today, who is Shiva Agrawal. He is instructor at Western Michigan University. Thank you, Shiva, for joining. And today
Thanks a
we are
lot.
going to talk very briefly about the Nobel Prize in Physics 2025. So, Shiva, my first question to you is, who got this Nobel Prize in Physics this year?
So, first of all, thanks for inviting me, and thanks for everyone to take out time to listen to this presentation. So, this year, the Nobel Prize was awarded on 7th of October 2025, and the Nobel Prize was awarded to John Clarke, Michel Devoret, and John Martinis for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So, first of all, John Clarke was born in 1942 in Cambridge, United Kingdom, and he is affiliated to University of California, Berkeley in California, USA. And his research interests are in superconducting quantum interference devices, which we also known as squids. Then Michael Devoret was born in 1953 in Paris, France, and he is affiliated to Yale University, New Haven in Connecticut, USA, and University of California, Santa Barbara, California, USA. And his research interests are in experimental solid state physics, and his emphasis is mainly on quantronics. Then the third Nobel Prize winner this year, John Martinis, was born in 1958 in San Pedro in USA, and he is right now affiliated to University of California, Santa Barbara, California, USA, and also with QLab in the Los Angeles, California, USA, and he investigates the physics of superconducting devices.
Nice. Thank you for that information. So, secondly, I want you to just share, or if you can describe their work, that what is the Nobel Prize given for?
Yeah, sure. So, first of all, to understand the work behind this Nobel Prize, we have to first understand quantum tunneling and what do we mean by quantum tunneling. So, in daily life, let's say if you are throwing a ball at the wall, then you expect the ball to bounce back, right? You can't expect the ball to go beyond that wall. But let's say if you are throwing a quantum mechanical particle, like let's say a proton or an electron, then you can still expect that particle to cross that boundary, that wall, or that barrier. This is what we know as quantum mechanical tunneling. We do not see all these phenomena in everyday life, but this is what we see in the quantum mechanical world when we talk about protons or electrons. Now, whenever we have a nucleus, we have protons and neutrons which are bind together. But what actually happens, a small part of those nucleus can still break off from the nucleus, and this is what we call as nuclear decay. Now, because the barrier is due to the attraction of neutrons and protons, the small particles which can break away happens through the quantum mechanical tunneling. So still there is a barrier, but the particle, like you see on your screen, the alpha particle can still break off from the nucleus, which happens due to the quantum mechanical tunneling. If the particles are bound very tightly, then it is very hard for the the nucleus to break. But if the neutrons, the protons are not bound very tightly, then the nucleus can still break, which happens in nuclear decay. And this is possible through quantum mechanical tunneling. And we also see quantum mechanical tunneling in our everyday life. And where do we see quantum mechanical tunneling? We use quantum mechanical tunneling in smartphones. So our smartphones are controlled by quantum mechanics. And there is a very nice video which you can search on YouTube, and you can understand how we use quantum mechanical tunneling every day in our daily life. Now, we need to understand quantization to understand this work. To understand quantization, first imagine a shop. It's a sweet shop, right? And you can go to this shop and you can ask for milk. Now you can ask, let's say, 1 liter of milk. You can ask 150 milliliters of milk. Let's say if some more family members are coming into your house, you can ask 2 liters of milk. And let's say if you have a small cat, you can ask 50 milliliters of milk, right? You can ask any amount of milk from the shopkeeper. But you can't do this with samosas, right? If you want to buy samosas, you can buy either one samosa, two samosa, three samosa, or what we can say, you can buy samosas as multiple of one. You can't buy half samosa. In the language of quantum mechanics, we call this quantization. The amount of samosas are quantized, or you can always buy samosas as multiple of some particular number. This is what we mean by quantization. So what in this figure you can see that initially we have the nucleus which can gain energy, right? It can jump from one step to another step by gaining energy. But the gain of energy is in a quantized manner. The nucleus cannot absorb just any amount of energy. It can always absorb energy which is multiple of some value. And this is how the energy of your nucleus will keep on increasing. And once you have enough energy, the particle can, the nucleus can break off. And this is how, at higher energy, there is more chance of quantum mechanical tunneling. Now we can talk about the experiment which these three Nobel Prize winners did. So you can see the setup, which looks like the one you see on your screen. And what they had a setup where they introduced zero voltage. And at zero voltage, they expected zero current. But they waited for their setup to show some voltage, which is what we see from quantum mechanical tunneling, that even if the particle does not have enough energy, it can still cross that barrier. This is what was seen in that experiment as well, that even when there was no current in the setup, some voltage was recorded. And the Nobel Prize winners, they also introduced microwaves. You can see the microwave contact, and they changed the wavelength of their microwaves. And as we know that wavelength is related to energy, by changing wavelength, they were changing the energy. And now their setup absorbed a specific amount of energy, which is what we saw in quantization. And what they observed that by absorbing this quantized energy, they could record voltage, which is what we expect from particle which absorbs energy, which is quantized, and moves to higher energy state. And this is what all was observed in the experiment in 1985. And this is the paper which you see from these three Nobel Prize winners. And interestingly, the paper came out in 7th of October 1985, and the Nobel Prize was awarded on 7th of October 2025. But the work was done in 1985, and this is how they reported their work.
Thank you, Shiva. That was really good. I learned new things today about quantization and also about the quantum mechanical tunneling. Thank you for sharing all that information. And then I think one of the last things I want to ask you for our audience to put in perspective that what is the relevance of these findings?
Yeah, so the work was done in 1985, but we still have relevance of this work even today and also in the future. So we talk about the importance and the future of this research. Then quantum mechanics is the foundation of all the digital technology. So as we just discussed that we use quantum mechanics in our cell phones in daily life, and it gives us opportunity to develop next generation of quantum technology. So the research that was done by the Nobel Prize winners is an opportunity for the next generation. Now, when we say the next generation quantum technology, we talk about quantum cryptography, we talk about quantum computers, and we talk about quantum sensors. Now, quantum technology has the potential to advance pharmaceutical industry, also to advance the agriculture sector, the energy sector, and the cyber security, which is important for security of all the digital technology that we see around us.
Nice. That was really good. Thank you for
Thanks.
sharing all the information, and I'm sure our audience will love this. It is a very simplistic view of what has been done. It takes a lot to have these findings, and I really appreciate your time and all the explanation.
And thanks for inviting me. And if you want to learn more about all these things, then these are some of the additional resources that you can take use of.
Thank you, Shiva.